In this graphic, I think it's really cool. As you can see, it's the top of many batteries. So, and again, Electrochem is going to be really cool because you'll actually understand really a lot of ways that you're using chemistry constantly in your daily life. So with Electrochem, we've got the study of the interchange of chemical and electrical energy. The basis of this is going to be a redox reaction. So all batteries, so you can think of, name as many types as you can think of, all batteries are chemical reaction that's producing electricity, which is really this transfer of electrons and doing some very useful work for you. So they are redox reactions at work. There are two processes going on with oxidation reduction. Oxidation is where electrons are lost by one substance, and reduction is where those electrons that are lost are gained by another substance. So that flow of electrons is what we're going to be using to do some work for us, like power your cell phone or your computer or a flashlight or anything. Oil rig is a great mnemonic device. Oil stands for oxidation involves loss, and RIG stands for reduction involves gain. And when we talk about loss and gain, we're talking about of electrons. That's the important key to redox, that flow of electrons. I like to use LEO. The line says GER. Either one, great, helpful instruments. LEO stands for losing electrons is oxidation. GER, gaining electrons is reduction. So just helpful things to remember so you won't get them confused. And again, since one substance adds another substance is gaining, we cannot have one without the other. So in a reaction, we can't have two oxidations, we can't have two reductions. We must have something being oxidized and another substance being reduced. So now that we understand how to assign oxidation numbers, you know what oxidation reduction are, we can actually talk about a battery that we mentioned at the very beginning. So first we're going to study one of the two types of electrochemical cells. These are really applications of how redox reactions are actually used. All batteries are called galvanic cells. Another term you might see is voltaic. I'll write that out. It's an older term. I still see it in textbooks and old AP questions, but it means galvanic, so either one is good. And batteries are made of, different components depending on the type of battery. Like your car battery is considered a wet cell battery, very different from dry cell batteries like AA, AAA, those kind of things. But the commonality between all kinds of batteries, no matter, it's just that even no matter what their components are, they all have in common that they're chemical reactions that produce electrical energy we're using to do some work for us. We will discuss the other type of electrochemical cell later. It's called electrolysis, or they're electrolytic cells. And this is really the opposite of a battery. This is like charging your cell phone, as you're taking electrochemical cell and adding energy to it. So completely different process, and will be discussed later. So for a galvanic cell, we're going to start off talking about the parts of it because it has some really important, and these might be new terms for you, but they're easy to remember. There's an anode. And this is the part of the cell where the oxidation process is occurring. If in the oxidation half reaction you have a solid metal involved, which in oxidation that solid metal would be a reactant, what's actually going to happen is the mass of that solid would decrease. Okay, so that's not going to happen in every cell, but if there is a solid involved in oxidation, that mass will actually be decreasing. And there's some really great mnemonic devices which do help a lot of students remember which process is occurring where. So anode is where oxidation occurs. So ox, it's kind of helpful. And then the other part of the galvanic cell is where the reduction process is occurring, and that is called the cathode. And when we have reduction, if there's a solid metal involved, that solid metal, since we need the oxidation numbers to go down, you would actually have, like if it's a metal ion, like we saw copper 2+, would gain 2 electrons to go to solid copper. If there is a solid metal involved, you actually would see the mass of that electrode go up because you're producing more solid as part of that reaction. So we call this the red cat because reduction occurs at the cathode. We do have an instrument that measures what we call cell potential of the battery. This is when you hear the word voltage, like a 9-volt battery. That tells us, and the voltmeter is measuring that energy that's traveling through the cell, and that's the energy we're using to do work. A wire would connect the anode to the cathode. The wire goes from the anode to the voltmeter and then to the cathode. And the electrons, and this is pretty important, you might want to put a big star by this, the electrons leave the anode, because think about it, the anode's oxidation, that's where electrons are lost in that half reaction. And the electrons are going to be traveling through the wire to the cathode where they want to be gained to cause reduction. And so the mnemonic device here is kind of a stretch, but flow of electrons is from the anode to the cathode. Now in a galvanic cell, and we'll see a picture of this in just a minute, but there's a pretty important component. Well, in fact, the battery cannot operate without this, but it's called the salt bridge. This is a connection, and it's a different connection beside the wire. They're two separate things. This connection between the anode and cathode is going to contain usually a dissolved salt, and it typically is a salt that is made up of spectator ions, meaning ions that aren't going to react with anything. We just want these ions to be present, and their purpose is, as this says, to maintain electrical neutrality. And really what that means is as electrons are leaving the anode and traveling to the cathode, you have this oxidation occurring in one half cell and the reduction occurring in the other. The ions that were previously dissolved in the solution become in different, the ratio of those ions changes, and we'll get into this detail in just a minute, but we need these soluble salts in the salt bridge to provide cations to neutralize the buildup of negative ions, and we need anions from the salt bridge to go to the other cell to neutralize or even out the buildup of positive ions. So the bottom line is cations from the salt bridge flow to the cathode, and anions from the salt bridge flow to the anode. The salt bridge, and examples I've used in the lab would be like a piece of filter paper that's been soaked in like sodium nitrate or potassium nitrate. There was a free response question where the salt bridge was actually a paste, electrolyte paste, and there are other labs you might do, Science of Motion has one where it's actually a porous cup so that the ions from both solutions can kind of go through the cup. But all of those are acting as the salt bridge. So KNO3 is a very good component. Again, we don't want ions that are going to cause other reactions. We just want those ions to be present in the solution, not to react with anything. Embedded is a galvanic cell. It's an animation, and it does a good job of discussing this new vocabulary of anode and cathode, and actually shows that the process is occurring at each electrode. I think it's really good. So look for what's being oxidized and reduced. Here is a similar depiction of what would be seen in the video. And the one thing I wanted to point out, because I think because we're used to seeing reactions where you add two things together and it produces products, This is a little unusual because all components, reactants, and products of the reaction are present before the reaction even begins. So I'm going to zoom in a little bit. Notice in this cell on the left, in the solution, we have zinc ions and nitrate ions, and then this piece of metal, and this is what I'm calling the electrode, that's dipping into the solution is made of zinc. Okay, so when we see a piece of metal dipping into a solution that contains its ion, those, you can tell the metal and that ion are going to be in its half reaction. And this is telling us underneath that beaker that zinc is being oxidized. Okay, and we'll see why in a minute. Also notice on the surface, the reason the anode is labeled as that piece of metal, that piece of zinc metal, that electrode, is because it's where the zinc is touching the zinc ion solution. On the surface of that is where that reaction is taking place. So notice what's happening is this solid zinc, you see the arrow, is going into the solution as a 2+ ion, and the electron is traveling, and as you can see above, it's the electron that's traveling. Electrons are traveling through the wire. That's your voltmeter with the value that's given in volts, and that's going to be traveling to the other side, to the cathode. Before we talk about the salt bridge, let's go ahead and look at this other side of the diagram, and it's telling us that Cu2+ is going to gain these 2 electrons to become copper solid. So again, where we have reduction is the cathode. These electrons show up here. What happens is, and you can see this in the diagram on the surface, that the 2 electrons on the surface of the copper come in contact with the 2+ ion. The ion gains the electrons and causes that ion to change to a solid atom, and notice it's plating on top of the existing copper that's already there. So when we talked about mass being increasing or decreasing if there's a metal involved, if we go over to this side photo, you can see that as the reaction would take place, the zinc anode, because the solid zinc is changing to a zinc 2+ ion after it loses the 2 electrons, the electrode actually gets smaller. Its mass decreases because the mass that's missing has gone into the solution as a 2+ ion. And notice the opposite's happening on the copper cathode. The copper ions from the solution are gaining 2 electrons and plating on top of that already existing copper. So that mass is increasing. So that was what was meant when I made those statements, just so you understand that a little bit better. Okay, back to our picture. We see this salt bridge is made of sodium chloride, and what's happening here, and I'll try to just give you a little bit more detail about this salt bridge, is, as I said, the anions, negative ions from the salt bridge will travel to the anode. Well, you know, again, it's to maintain electrical neutrality, but it's why. Why does it need to do that? Well, if you think about what's happening in the solution, before this redox reaction is taking place, in this solution you have dissolved, you see the salt that's dissolved, zinc nitrate. So for every 1 zinc 2+ ion, there are 2 nitrate ions. That's what's dissolved in the solution. Once this reaction starts occurring, the zinc, the solid zinc, is losing 2 electrons, and more zinc 2+ is entering the solution. So what's happening is we had this balance of zinc 2+ and nitrate ions, and once more zinc 2+ is going into the solution, the amount of nitrate ion is not changing, so we basically have this buildup of extra positive charges. This extra zinc 2+ is going into the solution. That's why anions, some kind of negative ion, is needed to neutralize that, because the electrons cannot leave. Think about it. Electrons are negative. If this is a buildup of positive, a negative would not be able to leave a positive buildup. So we need these extra negatives to flow from the salt bridge and be attracted to the zinc 2+ ions. They're not going to form precipitate or anything. They're just going to enter that solution. That allows the electrons to leave. So what's happening in the cathode compartment? Well, what's happening is that when the electrons come in, the copper 2 plus is attracted to those electrons, and as we said, is plating on top of the already existing copper as new solid. So what's happening if you go take a step back, in this solution, we've got this copper 2 nitrate solution. For every one copper 2 plus ion, there were 2 nitrate ions dissolved. So if copper 2 plus ion is leaving the solution, okay, what happens here is we're some of the positive charges are, becoming a solid, so there's a buildup of negative ions. So we need the cations, in this case sodium ion, to flow into the beaker from the salt bridge to maintain that neutrality. So that counteracts that buildup of charge. So that's the basics of what's going on with that salt bridge. And we're going to address what's going on with the voltmeter in just a minute. As you can see, this example is also giving you the balanced reaction at the bottom. And notice that, the zinc half reaction lost 2 electrons, the copper half reaction gained them, so it was easy to balance. It was just a matter of putting those two together because their electron transfer was already equal. And I just, as a reminder, I'll just kind of go through these as a reminder. If you have a metal dipping into a solution that contains its own ion, then those are going to be the components of its half reaction. Okay, there are cases that we will see where there are 2 ions in the half reaction, like we've already seen earlier. We had an Fe2 plus, I believe, and an Fe3 plus ion, or we'll see it later if not. See, neither of those are solid metal. So if both components in the half reaction are ions, they were both dissolved in the solution, and we would need an unreactive substance to we'd need the electrode to be made of an unreactive substance. So platinum is a choice, which is pretty expensive. In most cases, we would use something like graphite. Literally, you could take a piece of your, what we call pencil lead. It's really graphite, but you could take out of your mechanical pencil a piece of that lead and use that as an electrode. And that would be just a way for the electrons to get out of the solution. So again, I've kind of gone through all these examples. One thing to note is, nitrate ion that was part of that dissolved salt in the solution in both half cells is not part of the reaction. Notice that these are net ionic reactions. Nitrate ion is a very common spectator ion. It's not going to be involved in any reactions, and that's why it is not included in either half reaction, nor is it included in the overall reaction. Okay. When we get to questions to answer about galvanic cells, they've given us all the information. They've told us anode, they've told us cathode, they've given us the balanced reaction, the cell voltage, they've shown us how electrons are flowing. These are questions you're going to be able to answer from the information given. And again, I've included some questions that you really need to think about. How could I answer this? So how can we determine and label which half reactions could be oxidation or reduction? And this is really where this voltage comes in. With each question, you'll be given a table of reduction potentials, okay? And when we say potentials, think of voltage, okay? And we'll talk about this a little bit later too. These values, these voltages, indicate how likely a substance is to be reduced. So we're going to for each half reaction, we're going to have a voltage associated with it, and from those values, we'll be able to tell what's oxidized and reduced. And here's the key. The more positive reduction potential indicates the substance that will be reduced, and therefore whatever the other value is that's lower, that substance is the one that's going to be oxidized. So let's look at an example. So here we have the two half reactions that we just kind of looked at. Notice that they're both listed as reduction, and notice that's the title, standard reduction potentials. These are always typically given as reductions, And from this information, we can know what's actually going to be reduced and what half reaction would be reversed and become oxidation. Okay, so if you think about it, if you take any half reaction and you flip it, now you have, instead of having electrons on the reactant side, which indicates reduction, if we reversed it, we would have electrons on the product side. So as we said before, the more positive reduction potential for a galvanic cell will remain reduction. So notice for these two values we have positive 0.34 and negative 0.76. We can see that copper has a higher value. It will be the reduction. So this one will stay just like it is. Okay, nothing's going to change. That one's going to stay reduction. Now, the other half, again, we can't have two reductions. If something's gaining electrons, they have to come from somewhere, so we have to have oxidation. That tells us this lower value that we see here, that is going to be, have to be changed to be oxidation. So since it's a lower reduction potential, we're going to reverse the reaction like I mentioned. Okay, that's oxidation now. And the other key is, and you can't forget to do this, is because we've reversed this reaction, its potential changes sign. Okay, so now this is a reduction potential for copper, and now since we've reversed the zinc, this is what's going to be oxidized, and now we call that an oxidation potential. So how did we get 1.10 volts on the voltmeter? It's just a simple addition problem. We're going to get this standard, it's called standard cell potential, or I called it the overall voltage, same thing. We're going to take the reduction potential, which we see is that 0.34 volts that's listed in the table. Notice we're adding it to the positive 0.76, which is the oxidation potential once we reverse the zinc. That's how we got the 1.10 volts. And this is something you're going to be asked to calculate. And another question is, how do we get the balanced reaction? I mentioned this earlier. This balancing, is very simple. It's just a matter of putting them back together and canceling out your electrons, because the electrons were already balanced. Now, I'm not going to read through this again, but these slides explain exactly what I was saying about the salt bridge. It'd be good to read over that again and make sure you're understanding. The whole purpose of the salt bridge is to neutralize charges that are building up. So cations, and you need to mention the specific cation. So cations in this case, sodium ions will flow to the copper cathode, and chloride, the anions, will flow to the zinc anode. So again, it's a good general statement, cations to the cathode, anions to the anode. But if you're asked to explain that, especially like in a free response, you need to mention the specific anion that's flowing to what you're saying is the anode. In this case, it was zinc, and the specific identity of the cation and the identity of the cathode, in this case, copper. So, what if there's no salt bridge? This is a pretty common question that happens. If there's no salt bridge, the charges build up, the electrons cannot flow. So the voltmeter would have no reading. It would have a reading of 0. It would not be producing electricity. And again, this is just talking about that change in mass. Metals that are oxidized actually lose mass, and metals that are being reduced, that you're plating new solid on top of the existing solid. And this question is pretty important, and this was on a AP exam not too long ago. It says, where does the mass go? And there's some really interesting answers that came up with, but the key is ion. See, even though zinc has gone from solid to zinc 2+, it's only lost 2 electrons. When we do like the mass of an atom, we don't even consider the mass of electrons. Electrons do have mass, but it's just so small compared to the mass of protons and neutrons. So the mass of an atom comes from protons and neutrons. So if only 2 electrons are lost, the mass of the atom is remaining with the ion. So again, the ions are maintaining that mass. So the solid zinc loses 2 electrons, so the mass of the solid zinc electrode is really going into the solution as that ion. Now when we talk about, I've mentioned cell potential and voltage, here's really the definition of what that means. Cell potential or voltage is the measure of electromotive force. It's really the pull of electrons as they travel from the anode or cathode. It's that attraction that's pulling them. Common symbols are E cell, EMF you might have seen in other contexts. We're going to be looking at E cell or E naught cell, and we'll talk about that naught symbol in just a minute. But the unit is a volt, and it is that capital V. I've had students ask me, where are they getting these numbers from? So if you wondered that or not, it's pretty simple. It's just they took hydrogen gas as the standard, and they assigned its half reaction as a voltage of 0, and then they put every half reaction on the other, like as a galvanic cell, and they compared it to hydrogen gas. So if whatever was compared to hydrogen gas was reduced, it would have been a more positive reduction potential than hydrogen. And if something was paired with hydrogen gas where hydrogen gas was caused to be reduced, then that other substance was given a negative value. So the standard is hydrogen gas, and again, it's just everything, these values are coming from that comparison. Now, standard conditions, that is, every time you see this, it looks like a degree symbol, like degrees Celsius, but it's really pronounced not, and it means standard conditions. So when you look at standard reduction potential charts, they will tell you this was 1 molar solutions at 25 degrees Celsius, and that's why those pieces of information will be given, because that not symbol does indicate that specific lab temperature, that molarity for solutions. And if we had gases, they would be at a pressure of 1 atmosphere. So here's a good example for you to try. In this example, this will give you a good opportunity to try and see how you're doing on understanding this information. So again, number 1, determine the anode and cathode. Calculate the standard cell potential. Describe how the electrons will flow through the wire. Write the balanced net ionic equation. And number 5, describe how the K+ ions will move from the salt bridge. So you might pause and give yourself time to really answer all these questions specifically. So for number 1, we have these 2 reduction potentials given in the table. As we said earlier, the higher potential will stay reduction and the lower one will be reduced to be oxidation. So nickel would stay reduced and its value would stay that negative 0.25. The zinc half reaction would be reversed, and zinc would become oxidation, and we'll see that its cell potential will also be reversed as well. So the question is, what's the anode and cathode? The anode is zinc, since it had the lower reduction potential, so it is reversed, and nickel is a cathode, and it's reduced with the higher potential, and reduction occurs at the cathode. Number 2, this calculation, again, the nickel stays negative 0.25. We've reversed zinc to be oxidation. Just the addition of those two gives us this positive 0.51 volts. Number 3, how do the electrons flow in the wire? We know that they flow from the anode to the cathode, but we need to specifically mention that the electrons would leave the zinc, that because it is the anode, travel through the wire to the nickel cathode. A lot of free responses, they might actually ask you to draw this on the wire, like on the diagram. So you could just do arrowheads to show which direction they're going. For the balanced net ionic equation, and again it says net ionic because if you notice both solutions contain the nitrate ion, but as we said earlier, nitrate ion is a spectator. It's not involved in the reactions, and that's why it is not included in the half reactions nor in the overall balanced equation. Again, we're fortunate that the electrons are already, the number lost is equal to the number gained, so there's really no other adjustments except for just adding these together and not including the electrons. And 5, it's only asking about the K plus ion, so remember that's a cation, and just think cations, cathode. So the K plus ions would be moving from the salt bridge towards the cathode, in this case the nickel. So they're trying to neutralize the buildup of charge as the nickel 2 plus ion is leaving the solution as solid nickel. I want to take a minute and talk about non-standard conditions. We did talk about that not sign, which designates standard conditions. Well, what if we don't have standard conditions? And for electrochemistry, that's only going to be a situation where we have solutions other than 1 molar. The key to this is looking, because you'll have 2 ions typically. One is a reactant, one is a product. Could be more, but at least 2 ions. You need to know which ion is a reactant, which ion is a product, because we're going to make a ratio of these molarities. So the product, whichever ion is a product, and again brackets mean molarity, so whichever ion is a product, its molarity would go as the numerator in this ratio, and whichever ion is a reactant is going to go as the denominator in this ratio. What you're really looking for here is this ratio greater than 1 or less than 1? Okay, so if the ratio is greater than 1, okay, and this ratio is really called Q. I'm going to go ahead and tell you this here. Q is the reaction quotient. This really comes from a formula that is not required to be solved mathematically anymore, but you still are expected to understand the relationship. So again, back to, is the ratio greater than 1? If the ratio is greater than 1, what this is saying is that there are more products in the solution than reactants, so that overall the non-standard cell potential will be lower than the standard cell potential. So those extra products are preventing the reaction from going in the forward direction like it normally would have. So the measured voltage would be less. Number 4 just says, well, what if the ratio is less than 1? So what if we had 1 over 2? So that would be 0.5. If the ratio is less than 1, notice the reactants are in the denominator. So if the ratio is less than 1, the non-standard cell potential would actually be higher than the standard value. We have more reactants present than products, which allows the forward reaction to be greater and to produce more voltage. Now, where does this really come from? And it really comes from a formula called the Nernst Equation. It's not on the AP exam anymore, but if you kind of just look at this generally, it helps you understand why this ratio is such a big deal. And really the math explains it, everything on the other slide, a little bit better. Now this Nernst equation is valid for 25 degrees Celsius. There's also another version of the Nernst equation which has a few more variables, but at 25 degrees Celsius this version holds true, and this was the version on the previous formula sheet before they changed the exam. Notice here's our standard cell potential that we've been solving for. We're going to get to N. We'll see this in a minute. N, we always think of like in PV equals nRT, N is moles. For electrochemistry, it's still moles. It's just we're talking about moles of electrons. This is that balanced number of electrons. Okay. This 0.0592, this came from the temperature and some other constants. So that's just a derived value from some constants. And then here's that Q I was talking about. It says Q is the ratio of products to reactants. And really, technically to be correct, these are raised to exponents, and the exponents come from coefficients in the balanced chemical equation. And this is in the notes. Again, I do get my students to solve this a few times, and some of them try to remember the equation just because sometimes it's easier to explain if you're asked about molarities being changed. Instead of talking about it generically, they can just solve it and have, this non-standard E. It's just sometimes easier to talk about, is it greater than or less than the standard cell potential. But, that's kind of a personal preference. So what I was saying was, if Q is greater than 1, if you take the log, that's the logarithm button on your calculator, the log of a number greater than 1, it is a positive number. So then when you multiply times 0.0592, divide by the number of moles, that's a subtraction. So if you've gotten the log of Q as a positive number, even no matter what math you're doing, you're going to be subtracting from you're going to be subtracting this whole term from the standard cell potential. So, as I said on the previous slide, if the ratio is greater than 1, the non-standard potential is going to go down because it's going to be subtracted here. Okay? So if we plugged in a 2, you could do the math, and you would see that, whatever the standard cell potential was, you would be subtracting. Okay? Now, if we could talk about the other scenario, and I guess it's in the notes. If I plugged in a fraction, like if the ratio was 1/2, I'm really plugging in the log of 0.5. If I plug in a value that's less than 1 and take the log of it, and you can try this in your calculator, just plug in, hit log 0.5, and you'll see it's negative, or any number less than 1. What happens is, no matter what math we're doing in that term in parentheses, if you're subtracting a negative answer, you're adding. So that's why I'm saying that the non-standard cell potential will actually be higher when you have Q that's less than 1. So that's where that whole slide came from, just to get a little background information, and it's also in the notes. Okay, so we're back to talking about voltage and energy. There's a relationship you need to be aware of, and we've talked about what a volt is, but really kind of the details of it. So we have this electromotive force, which is what we call voltage, is equal to really work over charge. Okay, work measured in joules, and charge is measured in coulomb. So that might be a new unit. Notice these have been rearranged. The units have. So joule is equal to volt times coulomb, and then those are the abbreviations. And I'll just read this next statement. The work that can be accomplished when electrons are transferred through a wire depends on the potential difference, that's that EMF, in volts between 2 points in the circuit. And then 1 joule of work is produced when 1 coulomb of charge is transferred between 2 points in the circuit that differ by a potential of 1 volt. And a coulomb is just that quantity of electrons, which is the charges that are passing through the circuit. So just kind of background information. You just need to understand this unit relationship. Okay, so that just gives you a little bit of extra background so you'll understand those units, because we're about to apply that. Now, we have this concept called Gibbs free energy, and it will be discussed a lot in thermodynamics. So just for right now, just realize all we really need to understand about Gibbs free energy is the sign of it tells us if a reaction is going to happen or not on its own. Okay, so, and when we say a reaction happens on its own, it doesn't have to be fast. It might be a very slow reaction, but if a reaction is going to occur without outside intervention, that means it's thermodynamically favorable. The conditions are right for that for those reactants to form products. Okay, so here's what you need to connect. Thermodynamic favorability means that this term, delta Gibbs free energy, must be negative. Okay, so that just means a reaction is going to happen. Now, batteries, if they're connected properly in your calculator or, cell phone, whatever, those are chemical reactions that occur on their own. So we say galvanic cells, which are batteries, are thermodynamically favorable. Okay, so again, this is hugely important. It'll be covered in lots of different contexts throughout the year. Now, there are two formulas that deal with delta G that are related to electrochemistry. So we're going to go ahead and look at those, and you'll see why I had the slide about the joules and volts and coulombs in a minute. So here's the first one. And here are all the variables defined. So G is Gibbs free energy. N, we saw it's part of the Nernst equation. You are expected to know that. And all these are defined on the formula sheet as well. N is that number of moles of electrons that are transferred. This is the balanced number from the half reactions that cancels out. Because if we have one half reaction losing 2 electrons and one gaining 3, what would you plug in for N? You can't plug in 2 or 3. You would plug in the balanced value, which would be 6. F is a constant. It's called Faraday's constant. It's actually the charge in coulombs of 1 mole of electrons. So it's 96,485 coulombs per mole of electrons. So if we have 6 electrons transferred, 6 moles transferred, it would be multiplied, as you see, N times F. And then the last term we've seen already is that standard cell potential we've been calculating by adding the reduction potential to the oxidation potential. So if we go back to our nickel and zinc galvanic cell example that you worked on your own, our cell potential was 0.51 volts. So if you're asked what's the value of delta G, I just wanted to show you how you would plug in values and get the correct answer. So in both of those half reactions, we had a loss of 2 electrons and a gain of 2, so N is 2. Faraday's constant is from the formula sheet, and then we would plug in the cell potential we had added together to achieve. So you can see we've multiplied those 3 terms together. Moles of electrons cancel out, and we're left with volt times coulombs. And what does that equal to? That's a joule, which makes sense. That's an energy unit. And typically delta G is measured in kilojoules. In this case, unless it was specified, you'd be welcome to leave it in joules, or you could divide by 1,000 and get it into kilojoules. Both are correct. And another question that's very typical is this reaction thermodynamically favorable? If you're ever asked that question, you need to just know the sign of delta G. So in this case, we say yes, delta G is negative, therefore it's thermodynamically favorable. And then the other formula involves a quantity called K, which is the equilibrium constant. We know that galvanic cells, which are what we call batteries, are reactions that are occurring on their own. We know that reaction, those reactants are reacting together to form products. They're going forward. We call that a forward reaction. Another way to say that is that products are favored. And you'll see this. My pen's not working. Anyway, so I was going to write products are favored, but it's not working out right now. So just remember that if the forward reaction is favored or products are favored, we can speak of that in terms of this K. All right, and again, equilibrium is a huge topic in AP Chem as well. It's its own big idea, and that will be covered in great detail, but we can talk about it generally here as well. K actually has no units, which I know is super unusual because you're used to having to worry about those, but K really describes how the reaction proceeds and is this ratio of products over reactants. Now I know we've seen this before and we called it Q, okay, and again the products and the reactants both are raised to the coefficient in the balanced chemical equation. Okay, so both of these could be raised to a value based on coefficients. Now, what we're looking at here is basically what is the value of K. Just like when we said Q and K, and we'll get into this discussion in later units, but you know, Q was that ratio, K is the same ratio. The main difference is K, these molarities we know are at equilibrium. Q, it's unknown as to where the reaction is. So again, I know that's a lot of detail right now, but what you really need to worry about here is is K greater than 1 or less than 1? If we know a reaction is happening, that means the reactants are reacting and forming products. We know that's going forward. So this bulleted point here shows you if a reaction like a galvanic cell is going forward, it is producing a lot of products from the reactant. So that ratio is going to be greater than 1 because that means you have a lot of products over a diminishing amount of reactants. So the value of K can also predict the sign of delta G. So just like we saw in the first delta G formula, if we have a positive cell potential based on the formula, and we go back to that, if we have a positive cell potential, then we would have to have a negative delta G, because if you're plugging in a positive value here, delta G would have to be negative. And the same thing with K. If K is greater than 1, then delta G will also be negative. And we'll look at that formula right now. So here's the second formula. Delta G equals negative RT, and those are multiplied together, times the natural log of K. And let's go ahead and define these terms, and we'll talk about what natural log is. G is, again, Gibbs free energy. And we're, again, the sign of delta G will tell us about thermodynamic favorability. R, you've seen this before with PV equals nRT. It's the same R, except it's a different value than what we've used in gas laws. Okay, so be careful with this. There are several versions of R on the formula sheet. And since we're talking about energy, there is one gas constant that involves joules. And so 8.314 joules per Kelvin mole. So again, you just want to be aware of that, because you don't want to, it is a common mistake, unfortunately, that students will plug in the wrong value, and that just obviously is going to cause a lot of problems. T is temperature, so this RT is the same RT from PV equals nRT with the different R value. Ln is natural logarithm. This is a button on your calculator. It is, in my calculator, it's right below the logarithm button. It says ln. And it's just, as a log is a base 10, ln is not a base 10. It's just based on a different, slightly different. So, and then K is the equilibrium constant, which again, as we said, has no units. So if we know that K is greater than 1 and we do this math, delta G would have to be negative. If K is less than 1, and you could try this, you could plug in a number and try it, then delta G would be positive, which does tell us that this is thermodynamically unfavorable. But since we're studying galvanic cells right now, we know delta G is going to be negative because they are favorable. So again, if we go back to that example from before, here is the unrounded value we had for delta G. The temperature would have to be given, and it would be standard lab temperature of 25 degrees Celsius. And you would be asked to calculate the value of the equilibrium constant. We don't want to use unrounded numbers. It just introduces a lot of error. So notice I have the unrounded number. Here's my R value. My Celsius, 25 degrees Celsius, must be in Kelvin. And then we've got the natural log of K. So I wanted to kind of specifically go through this math, because you may not have used that. You may not be in the math yet where you have to use the natural log. So, I've divided RT to the other side. So once I do that math, I get the value of 39.72 equals ln K. If you look at your calculator, you'll notice right above the ln button is e to the x. What we're doing is we're taking this value out of this natural log. So the way you would type this into your calculator is you would hit second ln, and then that e with the flashing x would pop up. You would insert your 39.72, hit equals. Now we have the value of K, 1.78 times 10 to the 17th. K is much greater than 1. There's no doubt this reaction is going forward. So just as a wrap up, if we're going to have a battery or a galvanic cell, our cell potential has to be positive, delta G must be negative, and K is going to be greater than 1. Okay, now we're going to move on to the second type of electrochemical cell involved in electrochemistry. And it's an electrolytic cell, or you might see the process of electrolysis referred to. The best way to really start this is really to start from, what we've already studied. And so we've been talking about galvanic cells for a while. And so let's just look at these two pictures and really see what's the main differences that you see right off the bat. And this is a good way to, really we're going to be comparing and contrasting the two to see how they're alike and how they're different, because they do have some similarities as well. I think most students notice, first off, that, here with the galvanic cell, we have this light bulb, and then over here with the electrolytic cell, you have some kind of power source. There's some energy being plugged in. So I think that's obvious. A lot of times, this is supposed to designate a salt bridge, and as you notice, there's no salt bridge in the electrolytic cell. Some commonalities we'll get to is that they both have an anode and cathode. Electrons are still flowing. And then another difference you might notice, this is supposedly two containers, and this is one. So again, all this will be discussed as we go through the next few slides. Okay, so again, we've said most of this already. A galvanic cell we've talked about is, we're measuring the voltage it's producing, and then this is requiring power for it to work. We've got two containers versus one, salt bridge, no salt bridge. And if you didn't notice these signs, this is not something that's really important that you need to focus on, but I think if you've looked at like any battery, you notice it has a positive and negative pole. So a battery has a positive cathode, that's the cathode, and then the anode is negative, and it's just the opposite on our electrolytic cell. Other differences, and this is what is really what we're going to focus on. These are pretty important. These aren't as obvious you can't see these from the drawing. But if you go back to galvanic cells, and so far, every time we've looked at one, we've taken the highest or the most positive reduction potential, and that's reduction, and the lower value is that half reaction that we reversed to be oxidation. And due to that process, those first two things stated, because of these two, we had a positive cell potential. And because the cell potential was positive, based on that delta G formula, it's negative, and we just went over that K is greater than 1. So, because of, this process, it kind of led into all this other information. Now, this is where it gets, it's very different, okay? And you really have to focus on what kind of cell do I have. Mostly you're going to be looking at galvanic cells. Occasionally you'll see electrolytic cell. These are opposites. So if you think about them being opposites, that might be helpful. So for electrolytic cell, notice it says the most positive reduction potential and half reaction are the ones reversed. So again, hugely different. It's the complete opposite of what we're doing with a galvanic cell. So the lower reduction potential stays reduction. So when you take those two together and add them, you will always get this negative cell potential. And because that cell potential is negative and you plug it in that delta G formula, you're going to get a positive value. And then K is going to be less than 1, because this is a reaction that favors reactants. It's that energy you're adding, you're forcing it to really a non-favorable reaction to happen. Okay, they do have a few things in common. Oxidation is still at the anode, reduction is still at the cathode, and electrons are still flowing from the anode to the cathode. So everything's not opposite. So I just wanted to point that out, because sometimes students assume that everything is kind of backwards, but the anode is always where oxidation occurs, and the cathode is always where reduction occurs. And again, this is just kind of a summary of what was in the other table about these signs of these quantities that you'll see and be asked about. And so let's look at an example, because it's great to look at all the information, but you have to be able to apply it for yourself. So Here are two different half reactions. You can tell they're half reactions because we see electrons. You can tell they're both reduction because those are electrons as reactants. So if you were asked to write a balanced net ionic equation for the electrolysis reaction that would occur in the cell, so that tells us what we need to adjust. So again, think about how you're going to use those values. If it's electrolysis, then you're going to calculate the cell potential and answer, is this going to be thermodynamically favorable or not? So take some time and work through those three questions. So if this is electrolysis, the lower reduction potential will stay reduction. So that means we're going to leave this just like it is, and we're going to take this higher potential and reverse it and its sign. And it's like I've actually done 1 and 2 out of order, but again, you'll have that same information. So this is staying reduction. We've reversed this to be negative. Once we add those two together, we do get the expected negative cell potential of and it is negative 8.89 volts. So for the balancing for this, again, the oxidation, this is the half reaction that's going to get reversed since it's higher, and this is electrolysis. It has a transfer of 4 electrons, so that causes us to double the copper. And so when we add those together, we end up with 2 water molecules, and 2 copper 2 plus ions yields oxygen plus 4 H plus and 2 copper solid atoms. And then the third question, was this thermodynamically favorable? And the answer is no. Since the cell potential is negative, that would also cause delta G to be positive. That will be corrected. So this is a positive delta G, and that's why it's thermodynamically unfavorable. And the last topic we'll talk about is electrical current. And voltage and current aren't the same thing. And so we need to define current. Current is really a rate. It's how many coulombs of charge, which are electrons, pass a given point per second. Its symbol is a capital I. This formula is on the formula sheet. I equals Q over T. So current equals quantity of charge per time. Then you've probably heard about current because you've heard of amps, AMP. And then amps are really, if you remember what Q, we talked about coulombs earlier with Faraday's constant, but amps are coulombs per second. And so you will see this a lot. So just remember, this is pretty important. Amps are coulombs per second. That is also on the formula sheet, so that will be helpful. Okay, so here are the questions that you could possibly be asked some portion of these. So how long must a current be applied to a solution to plate out a metal, or what mass of a metal will plate out if a current is applied to a certain amount for a certain amount of time? So we can do dimensional analysis to answer these. So how long must a current of 2 amps be applied to a solution of silver ions to plate out 11.5 grams of silver metal? Now this is a time question. So again, if we think about our, that we're given amps, that is where our time unit is going to come in. So that's really a calculation we'll have to do at the end to answer that question. What we really need to know is based on how much silver is expected to be plated out and the electrons involved, how much charge is going to be involved. So we really need to focus on finding these coulombs. Okay, so if we start with mass, every time we have mass, pretty much always we change it to moles. Okay, since this is a silver +1 ion, there's only 1 mole of electron that's going to be involved in this half reaction. So for every 1 mole of the solid, there's 1 mole of electrons. And then this is where you have to remember to use Faraday's constant. This is the connection between the half reaction and the quantity of charge. So by multiplying times Faraday's constant, now we have coulombs, and then we can plug into the formula. You could have gone on with dimensional analysis. I'll just show you that. Instead of doing this other set, you could have actually plugged in 2.5. We said it's 2.5 amps, which is also 2.5 coulombs per second. So if I invert that, so coulombs cancels out. I would divide, and then I would also have seconds the same way. So again, you can use the formula or just continue with dimensional analysis. It works both ways. There was not a time unit specified. I just changed it to minutes because that's kind of an unusual number of seconds. But again, if no time unit is specified, it would be fine to leave it in that unit. Number 2, the other version of this is really the same question going in reverse. What mass of copper metal will plate out if a current of 4.5 amps is applied to a solution of copper to nitrate for 35 minutes? In this question, we know time and current, so that is a way for us to know our coulombs, our quantity of charge, and from that we can work towards, with Faraday's constant, electrons, and then change moles to grams. So notice I used the formula here. I plugged in my amps, and I changed my time from minutes to seconds. And so I multiplied to get 9,450 coulombs. And here's my Faraday's constant again. If we have coulombs, we can make a connection to our half reaction and the electrons. So dividing by 96,485 coulombs, that gives me 1 mole of electrons. In this half reaction, since it was copper 2+, we know 2 electrons are involved, whereas we only had 1 with the silver ion because it was +1. So we're dividing by 2. Once we have moles of copper, we can use the molar mass and get the mass of copper.